In the previous lecture, we have seen that the time complexity of beta is equals to x transpose x inverse x transpose y in real life scenarios goes nearly about 10 to the power 17 operations. This is a hell lot of time. So, are there any other better approaches to finding these values of beta? Yes, and that is known as gradient descent. So, what comes to your mind by the name of this gradient and descent? Something related to graph functions? Yes, you're absolutely right. Well, we know that our loss function is equal to sigma of y minus y hat whole square, and our objective was to minimize this loss as much as possible using differentiation. But if we plot this loss function on a graph, then we get a graph something like this. If we assume these are going to be the x values and this is the loss value, it will come out to be a curve. It looks like a upward parabola because here, as you can see, the degree is 2. As you can see here, the loss function is minimum. If we assume these x to be the values of beta, then this is our required value of weights or beta values in our regression function. How do we reach this? We have our formula, this one, but it consumes a lot of time to compute it using this. So what are we gonna do? We will start from a random x. We will initialize beta with any value. I mean, like, let's take this value, or more better would be, assume we started with this random values of beta. Okay. Now, our goal is to move down this curve to this beta, which is the beta min. How can we achieve that? If we observe closely, here the slope of this graph is positive. Since tan theta is less than 90, and we can see from this x-axis that beta min is less than beta. So what can we do? We want to move downwards. So we can write beta new equal to beta old, which is this current point, beta old minus, because we are going towards the left side, we are decreasing our beta value, beta old minus what is the value of derivative of this function at this point. It is nothing but dl by d beta at beta old. This is the equation we wanted, but there is a small catch here. What if this dl by d beta is so much larger than this beta old? Then we might jump to this point, right? So we will control this term using another term known as eta, which is learning rate. So now finally our gradient descent function is going to be beta new equal to beta old minus eta times dl by d beta at beta old. This is the equation we wanted. Now let's do a question on this to get habituated for practice. Let's assume our loss function is 15 plus 20 beta naught square plus 15 beta 1 square plus 30 beta naught beta 1. Just a disclaimer, this beta need not be a point, it can also be a vector. We are dealing in n dimensions. Beta can be an order of n into 1 matrix, which is a vector of n dimensions and one column, which is basically one vector. So 30 beta naught beta 1. Now as per this formula we can see that we need the value of gradient here. So first let's calculate this dl by d beta. dl by d beta, this is equal to, since beta is a vector of two dimensions, how can we tell that they are two? Here we have two terms, beta naught and beta 1. So our vector is going to be del L. We have to take partial derivative. Del L by del beta naught, del L by del beta 1. This is equal to del L by del beta naught. So other terms except beta naught are going to be assumed as constant. Since this is constant, derivative of constant is 0 plus, differentiate this normally, 2 20 beta square beta 20 beta naught square is going to be 40 beta naught plus this is a constant plus 30 beta naught, so 30 beta 1, and this bottom one with respect to beta 1 constant 0 constant 0, this is 30 beta 1, 30 beta 1 plus this is beta 1, so it's going to be 30 beta naught. So our derivative value is going to be dl by d beta is equal to a vector of 2 cross 2, 40 beta naught plus 30 beta 1, 40 beta naught plus 30 beta 1, 30 30, 30 beta 1, 30 beta naught plus 30 beta 1. This is our derivative. And let's assume our initial point beta ini is equal to 1 comma 1. That is, we are starting with initial values of beta as 1 and 1, and also our learning rate to be 0.1. Yes, so beta new equal to beta old minus del L by del beta at beta old into eta. So beta old is 1 1 minus, now just put this 1 1 in this place. So we are going to get, so this above one is beta naught and below one is beta 1. So if we put this point here, 40 plus 30 is going to be 70. This is 30 plus 30, which is going to be 60, into eta is 0.1, which is 1 by 10. So we will get 1 minus 7 by 10. 7. This is 1 minus 6, which is equal to minus 6 minus 5. Now this is just next step of beta values, but we haven't reached that minima point. We have to do this process again and again until we reach the minima point. How will we know that we have reached this minima point? the gradient, that is del L by del beta, will eventually tend to 0. That time we can be sure that we have reached beta min and we can stop our iterations. Of course, this will take a lot of iterations, maybe in thousands or 10,000s. We can't do it manually, so we have to use a computer program to do it. For now, we'll just stop after one iteration, and with beta new values is equals to minus 6 and minus 5. That's it. Thank you.